Okay, Morgan. Yeah. So let's talk about a new concept today, and basically we're temporarily moving back to sort of like a time domain. Okay, we'll look at essentially the mapping from S-plane to Z-plane. And the purpose is mainly for the pole placement in the discrete when you design a discrete digital controller. So here's a bigger picture. Okay. Yeah. Now this one shows you. This is basically the location of a pulse in S-plane and its corresponding response. Okay. So for example, if you have a pole at here, then this is basically like you have 1 over S plus A, a location at here, right? Yeah. And its impulse response is this shape at here. Okay, right? So apparently every pulse on the left side is stable, and they're all non-stable at here, right? Yeah. So the idea is basically we know very well of the response of those pulses in S-plane. So when we design a digital controller, or when we discretize the things, so you don't have an impulse sampler, okay? Then any one of these response will become a discrete sequence of numbers. So the question is, how does the system respond, right? Basically in the Z-plane, okay? And where does the pole is mapped to, right, in the Z-plane? Okay, so that's basically the idea of this lecture here. We're looking at the mapping. Okay, yeah. The way we do the mapping is basically we need to stick to the simple relationship, okay, because of the impulse sampling, okay, and that relationship is Z equal to e to the power of st, right? Okay, that's what we need to stick to. Okay, so now let's move on here and look at the details, okay, of the mapping. So first one, let's look at is let's look at in general, right? Let's look at in general because we're really interested is the mapping of the left side of the plane of the S plane, okay, left half of the plane of S. Okay. Okay. So left half of the plane meaning what? Your pole in S plane in general can be written as sigma plus j omega, right? So for example, if I pull it here and the corresponding value, this is sigma and this is omega, right? Yeah. So then when we do the mapping, or when it's in the first of all, if it's in the left half of the plane, so that means the sigma is going to be less than 0, right? Yeah, that's the first thing. And second of all, we do the mapping, so e to the power of st. Okay, so given certain sampling time, okay, let's see where does the pole, okay, is mapped into. Okay, let's plug the s over here. Okay, so with the pole in S plane, this is the pole location in the Z plane. So what's the value of this? This is basically sigma times t plus j omega times t, right? So this is sigma t plus j omega t, which is e to the power of a times e to the power of b. Okay. Yeah. Okay. And then e to the power of sigma t, this is the real, right? This is a real number. And e to the power j omega t, this is a complex number. And the complex number basically, this is like a cosine omega t plus j sine omega t, right? Yeah. And as we know that you multiply when you add a multiple of this 2 pi, right? It doesn't change. So sine theta plus 2 pi is still the sine theta. Okay? Yeah. So now let's manipulate this one just a little bit here. Okay? We'll take the sampling time t out. This is omega plus 2 pi over t times k. Okay? Right? Yeah. So then what is 2 pi over t? T is sampling time. So 2 pi over t is what? The sampling frequency, right? Plus k. Okay? So that's all the manipulation we need to look at it. So basically, when you have S-plane pole with the mapping, here is the nature of the mapping. Okay? Yeah, in general. Okay. So what do we observe at here, right? What do we observe at here? Which means what? Which means, okay, first observation, I'll draw a diagram right here. Okay, so you look at this one here, okay? What does it mean is basically when you set k equal to 0 or when you set k equal to 1 or 2 or 3, they all end up with what? The same z, right? They all in the same z. So essentially, let's say if this is your S here, this is your sigma, and this is your omega, okay? This is your omega here. And then we're going to do the mapping. So we're going to do the mapping, map it to the Z plane. Okay, yeah. So this guy will be mapped, I don't know, maybe somewhere over here. Okay, right? Yeah. And now, if you look at the nature with the e to the power of st, okay? So what does that mean is, this is omega. Now, if I change this omega to where? To this location, let's say. And this is omega plus omega s, right? Without changing the sigma. It's still the sigma at here. Is that okay? So guess where does this guy map to now? The same location, right? Same location. And of course you can move it down a little bit. So basically as long as what? As long as they are separated, right, by an interval of omega s sampling frequency, they are all going to be mapped to the same location in the Z plane. Okay, the same location in the Z plane. Okay. Yeah. So this is basically the first observation here. The first observation is essentially, as I said, as long as a interval of omega s, okay, in S plane, okay, they all mapped to same location in Z plane. Okay? Yeah. That's the first observation here, okay? Yeah. Second observation. So essentially, in other words, you have actually infinite number of pole location in the S corresponding to one location in the Z plane. Okay, yeah. Second observation is we're assuming the location of the pole is in the left half of the S plane, so sigma is less than 0, right? Sigma less than 0. So after the mapping, your pole location in the Z is this quantity, or this quantity, doesn't matter. Okay, yeah. Now, if the question asking is, so what's the magnitude? This is basically this is a complex number, right? Either way, this is a complex number, and you can always say, so what's the magnitude, right? Magnitude is the R and then theta, right? Yeah. So theta apparently is omega t, or theta is this. Okay. Yeah. And R is what? R is basically the whole thing, the magnitude of the whole thing here, right? Yeah. So this could produce, sine theta could cosine theta could produce a negative number, right? Yeah. But the whole thing, the magnitude, the whole thing is basically the magnitude of this quantity here, right? Yeah. So basically, the second observation, the R, okay, is to the power of sigma t. I didn't put the absolute value at here. The reason is because e to the power of anything is naturally a positive number, right? Yeah. And sigma here, guess what? Sigma here is less than 0. Okay. So this is basically an exponential decay function, right? Exponential decay function. And if you change the t, the way to change it, but when capital T equal to 0, capital T equal to 0, actually, it's almost impossible, right? But this is basically guarantee that this is what? Less than 1, right? It's less than 1. Okay? Yeah. So basically, your absolute of Z, which is equal to the R to this quantity, is less than 1. Okay? Less than 1. Okay? So that makes perfect sense. What we're looking at is the left hand of the plane. And now it's everywhere, okay, in the left side of the plane will be mapped in the Z plane with a magnitude of the pole less than 1. So basically, which means what? This is a unit circle, right? This is a unit circle here. Okay, so it's all going to be mapped inside this one here. Okay, yeah. Okay, and it's stable. So right, and we have already observed, because in the Z plane, when you have a Z over Z minus A, as long as the A absolute value of the A is within the unit circle, then this is a stable response, right? It'll be a decay to 0. Okay. Okay. So and then we can take a look at another observation at here. Okay. So one more here, and this observation here will end up with this concept called primary stripe, okay, and a complementary stripe. Okay, and this observation is very much similar to the first one over here. Okay, so it's the first one. Okay, so let's basically essentially look at some maybe a specific examples now. So if S equal to sigma plus j omega, just rewrite that, e to the power of st, okay, and e to the power of sigma t, okay, e to the power of j omega t, okay, yeah, like this. So let's consider this. Let's consider sigma equal to 0, specific case. If sigma equal to 0, that means the pole in the S plane is actually on where? On the imaginary axis, right? Imaginary axis, okay? So basically, if this is the S plane, so now we're looking at is a pole on the imaginary axis. Okay, so this is imaginary axis, real axis. Okay, and then the Z will turn into e to the power of j omega t, right? E to the power of j omega t. If z equal to this e to the power j omega t, and which means the magnitude is 1 and the angle is omega t, right? Omega t, okay? Yeah. So, which means what? Which means that particular pole will be mapped to where? Exactly, right? Basically to somewhere on the unit circle, depends on the value of omega t. So omega t is the theta, so maybe it's going to be mapped over here with an angle of omega t. Okay? Yeah. That's the z plane. Yes. Okay. Yeah. So everywhere, right, on the S plane will be mapped to here. However, if you remember the first observation at here, you actually have a sort of a repetitive pattern here, right? As you're going along, they all map to the same location. Okay? So what happens is, let's consider this. Let's consider we are moving from, let's say, negative j omega s to over 2. Okay? So this is a negative j omega s over 2. And then 2 to where? To a positive j omega s over 2. Okay? So let's see what happens if I move from here to here. Okay? Like this. So if I move from here to here, let's first look at the boundary at here. So where does negative j omega s over 2, right? Where is this guy going to be mapped to in the z plane? Okay, this location. So how do we verify that? So what do? We use this equation at here, right? Use this equation. So at negative j omega s over 2, okay, at this location. Okay. In other words, basically when omega equal to negative j omega s equal over 2, negative j omega divided by 2. Okay. Yeah. Then where does the z map? So z equal to, it's still 1 at here. It's just e to the power of j times what? Times this whole chunk here, right? Times this whole chunk. So omega, not j, right? Omega equal to negative omega s over 2. Okay, so this axis is j omega axis, right? Yeah, j omega axis. Okay, so basically I replaced omega with negative omega s over 2 times capital T. Okay, yeah. And what is the relationship between omega s and the capital T? So 2 pi over capital T is omega s, right? Sampling time. Okay. Yeah. And so what does that equal to now? So this equal to e to the power of negative j pi, right? So we're like g pi. So where is e to the power of negative j pi in the z plane? So where is it? Theta says theta equal to negative pi. So basically, where is it? It's this is negative pi, right? Essentially, it's where? It's this, right? It's this location. Okay, it's this location. Okay, so this point is mapped to here. So now let's move up, okay, like this, until this location. Then at omega equal to omega s over 2, can you take a quick guess, or even just look at this. Where would that be now? E to the power of j pi, right? G pi. And where is e to the power of g pi in the z plane? Where is it? Same location, right? So remember what we did in the S plane? We're moving up here. So in the S plane, as you're moving up here, you can't move away from where in the Z plane? You can't move away from the unit circle, right? So it doesn't matter how you move here, you're still going to be on the unit circle. Now as you're moving from here to here, so basically it's like you're tracking this circle going all the way from this location and then back to this location. Okay? Yeah. That makes sense? So basically, as you're moving here to here, you're circling basically one round at here. Okay? One round. Now imagine what you do next. Let's say if I keep going from here, going up to where? Maybe up to the next j times omega s. So basically, next from here, I'm going to add 1 omega s here. So 3 over 2. Remember what the first observation? When you add the omega with omega s, right, by interval omega s, no change, same mapping. So if I do the same thing, if I do from here, I add 1 omega s here, so that's this location, right? So the interval basically between these two is omega s. And the second interval here is another omega s. So guess what happened now? If you move from here to here, so from here to here, I can summarize as omega changes from negative omega s over 2 to omega s over 2. Okay, we get the z changes from negative pi to pi in z. If you go again, is omega s over 2 to 3 omega s over 2. So can you imagine how does the theta angle changes in the z plane? So it should go from pi to how much? 2 pi, right? Okay. So 2 pi? No. How much? 3, yes. Okay, 3 pi, right? So basically you're going another round here, 2 pi, right? Yeah. Okay, so essentially on the g omega axis, right? On the g omega axis, I can separate the g omega axis. I don't need to look at all the g omega axis, right? In theory, I only need to look at this portion here, because that pretty much covers the whole unit circle now. Okay, yeah. Good point. So where would the origin, right? Okay. So now let's do this now, right? Let's do this. So now you move from here to here. Okay. Maybe let's label a couple of things that are here. So I should have drawn a better one in here. Okay, so let's say you move from here to here, and then from here to here, and then we are going to move, okay, all the way to the left. Right? So up to here, all the way to the left. When you go all the way to the left, what changes? What's not changing? In terms of this S equal to sigma plus g omega. So as you're moving along this horizontal line here, which 1 is changing. Sorry? Omega 1 is not. Omega is not changing. So sigma is changing, right? And sigma is getting what? Smaller and smaller, right? It's negative number, so it's smaller and smaller. Okay? Smaller and smaller. So then this is the mapping at here. And guess what happened to the magnitude? And it's gonna be go back to 0. So basically, if you move, so this is what happens, right? You started from here. Let's say this is location A, this is B. Now you all the way to the infinite C. So this is A at the bottom here, all the way to the B, right? And then from the B, as you move into that direction, you're essentially, you can imagine this is from B to C. First of all, from B to C, does the theta angle change? So you know when you're moving from B to C, because omega is not changing. So after the mapping, what's the theta? Theta is always omega t, right? So actually theta is not changing at all, right? So it's all it changes is this magnitude. So basically you're like from B location tracking along the real axis at here and then moving back to the C location. But I put a C on the top of the axis here, okay? On top of the axis. So as you can see in my lecture notes, the way I draw probably is better is, you know, just explode it a little bit, and A is over here, and B is just about to, well, it's technically it's gonna be on the axis, but it's going to go back to 0, okay, like this. Was all right? Yeah. Okay. And this is the C location, right? This is C here. Okay. So if I complete this this trajectory with this symmetric thing, so let's say I'm going from infinite left side D to A. So where do you think the D location is? Pardon me? Origin. But it's not going to be the same as C though, right? The angle D at the location, after the mapping, the theta for the D should, the theta for the C is what? Whatever the omega t is, right? Yeah. And but if I draw this from here, so it's actually going to be pi. Okay. So but the D is actually the same as A, it's going to be negative pi. So the D location should be, right, still at the origin, but it's the bottom at here. Okay, it's the bottom here. Was all right? See, that's essentially this whole chunk. This whole chunk, you can consider it's a stripe. Okay, that's what we call the primary stripe. Okay, primary stripe. So what would be the complementary now? Complementary meaning you move up with one notch, and you can draw another stripe, right? So that stripe will be mapped as the same as this, right? It's just going around one more round of the circle. Okay. Yeah. So this is primary, and this is complementary. So then you can draw another complementary. So there are infinite number of complementary there, but there's only one primary though, right? Okay. Not necessary. But all you need is you just need to know that when you pick the pose in the S-plane, right? You just need to bear in mind there are infinite number of poses in the S-plane that will be mapped to the same Z-plane. Okay. Yeah. So when you pick the pose, you don't need to say, oh, I'm going to pick a pose at here or at here, right? They're actually the same thing basically after the map. See, right? Yeah. Okay. Well, I guess in a sense you're right. So you're just basically going to focus on the primary stripe, okay, the location of the primary stripe. Okay. A quick question. where does the origin, where's this origin map to? The origin S-plane, yeah. On the unit circle, of course, yeah, because the g omega axis on the unit circle, but where exactly? Here, right? Yeah. Okay, so this is, or if this is a O here, and that's your O as mapped to here. Okay. All right, good. And the other thing is, I think it's a little bit related to what I touched upon at the end of the lecture in the previous lecture. So, when you move from A to B, now at the A location or at the B location, we understand that this is A location, this is B, right? So the angle is negative pi, the B, and the angle is pi. Okay, B is pi. So basically z equal to positive negative pi. Okay, positive negative pi. Now, what's the positive and what does positive and negative pi means in terms of this? In terms of the response. See, this is theta, and when you're moving back to this to the discrete sequence, it's actually what? Cosine theta times k, right? Cosine theta times k. So if theta equal to pi, it's cosine k pi, right? It's cosine k pi. And what is cosine k pi again? Let's see. Negative 1 to the power of k, right? So the response is essentially it's like what? Going up, going down, going up, going down. Okay? Up and downs like this. Okay? Yeah. So that's the nature. Basically at A and B location, the pole at A and B location, the response at this location is inherently inevitable. Is going to be up and downs like this. Up and downs, you know, the first time is up, the next time is down. If you recall in the previous lecture, what do we say? That's the highest frequency that you can experience, right? As a discrete sequence of number. Okay? Highest frequency. Okay. So in other words, somewhere around here, okay, somewhere around here, you would imagine that I would expect maybe may not be even exactly at this location. At exact locations up and downs, but if you move away from this location a little bit, it's not going to be immediate up and downs, right? But it's going to be maybe up and then all the way back almost to zero, then negative, more negative, then back. So basically, there'll still be pretty high frequency of oscillations in terms of the discrete numbers, right? So this region here, around this pi or negative pi location, this is in general what we call it's high frequency. And the high frequency is in terms of the sequence of numbers. Okay, not exactly it's a high frequency idea in the continuous system. You know what I'm saying? Okay, so this location here, you can see that's a sort of a high frequency region. Okay, high frequency region. So similarly, then for this region around this zero location, so that's going to be a low frequency region. Okay, low frequency. Okay. So as a matter of fact, if you pick somewhere around here, you don't really see any oscillations at all, right? Yeah. Probably all you see is just exponential decay. Okay. Yeah. In terms of the sequence. Okay. Okay. So now we have a sort of an idea now in terms of mapping. Okay. And what we're gonna look. Yeah.
I was just going to say, if you were to go, say, to a higher order, like 3 pi over 2, like normally in the S-plane, the further you make poles apart,
In the S-plane?
Yeah.
So you mean one is
Spread
here?
those poles apart further, it becomes more undamped, right? But you can't see that in the Z plane, can you?
No. So that's the thing here. You know, your thing is in the S-plane, the poles that are here, the poles that are here, the poles that are here, they don't exactly exhibit the same kind of response, right? That's true. Okay? That's true. Okay? So what makes this, after mapping, they all become the same thing now, right? The reason is because you're sampling time. Okay? You're sampling the different time. And actually, in the background and here, it's the idea of that alias. Right? The alias problem. So you see, remember, you have a sinusoidal signal. Okay? Let's say if you sample it at a certain sampling time, you get a sequence number, right? If you sample at another sampling time, as a matter of fact, even if the second sampling time is maybe much smaller than that, you may end up with the same sequence number as the previous one. That makes sense, right? Yeah. What does that mean? That means that the alias, right? The second sampling time is the alias of the first one. But doesn't mean the second sampling time, right, will give you the enough information for you to reconstruct the original signal, right? Yeah. So, but as a digital signal, you don't know where the number is from, right? So after sampling, all you see is just sequence numbers. You see what I'm saying, right? Yeah. So it might be from a useful information. It might be from, you know, totally garbage information, right? Yeah. But mathematically, right, in terms of mapping, that's basically what happens. You see what I'm saying, right? Yeah. Okay. Excellent. So that actually basically brings the question is, you know, we can't forget the continuous system. You know, everything basically originated from your continuous system, right? So your starting point is always a continuous system. When people say, can you design a system, you know, with a certain kind of specification, your first thing coming to your mind is continuous system pole, okay? Not the Z-plane pole, right? And then if you're designing a digital controller, and then you basically to start to map from the continuous pole location and to the Z-plane, right? So this is essentially the next thing at here is let's do a quick review in terms of the continuous system at here. Okay. Yeah. We're not reviewing, you know, all continuous system. So we're essentially going to look at the very typical representative type of a system, which is a second order system. Okay. Yeah. So what is a second order system? It's this transfer function. Okay. Okay, it's this transfer function. So omega n squared over s squared plus 2 zeta omega ns plus omega n squared. Okay. Yeah. So let's suppose this is a transfer function. Maybe this is basically input over output, right? Yeah, who knows? Okay. So for this particular second order system, you know, people always basically summarize the response, some of those characteristics out of the second order system, right? First of all, where is the pole location for the second order system? As you probably know, this is a damping ratio. This is the natural frequency, right? Yeah. And the pole of this system is S1, 2. There are two complex poles in general, and zeta omega n negative plus minus j and omega n over 1 minus zeta square. Okay, zeta square. Okay, that's a second order system. Okay. All right. So you can actually, if you want to rewrite this second order system, it's equivalent to this one here, omega n over 1 minus zeta square. Okay, and then omega n times root 1 minus zeta square over S plus zeta omega n square plus omega n square 1 minus zeta square. Okay, so that's your h of s. And if you set the denominator to be 0, you get the pose like this. Okay, get a pose like this. Okay, so typically what we call this, we call this a sigma. This one here we call that omega d. Okay, this one called omega d here. So omega d here is called damped natural frequency, right? Yeah. Okay, damped natural frequency. So zeta is the damping ratio. Okay, omega n is the natural frequency. Now, given this second order system, so people look at the impulse response and step response of the system. Basically, when your input is an impulse input, right, that's your impulse response. When your input is a step input, then that's step response. So by changing the zeta and the omega n, you will have different basically curves, right, response for this impulse and step. Then we can summarize some of the natures, right, out of the typical second order system. So the first one is impulse response. So impulse response, when your input is the impulse. The impulse response is basically what will be the output when the input is the impulse. So it's actually basically what we're gonna see is your output y of t, okay, is actually just gonna be the inverse Laplace, okay, of h of s, okay, impulse response. Yeah. If you look at your handout, okay, if you look at your handout of the Z transformation table, if you look at your handout, you actually will see that there is one particular transformation, and that's omega over s plus a square plus omega square. Okay, you have one particular item like this, and the corresponding mapping. Okay, so if you look at this, the writing I have over here, what is that? That's exactly the same format as this, right? What's A? A is that omega n. What is omega? Omega is the square root of this guy here, right? What's this omega? Omega is this guy here. See, this one is the square root of this. Okay, yeah. All right, so you can easily find the inverse Laplace using the table, and the inverse Laplace you get is this: omega n over 1 minus zeta square then time e to the power of sigma t sine, okay, omega dt, okay, sine omega dt. That's the impulse response. Okay, so sigma, right, is a negative zeta omega n, so sigma is a negative number. So which means this is going to be an exponential decay function. Sine, that's a sinusoidal function, right? Yeah. And in essence, what you're going to see is, okay, this is sinusoidal. Typically, it's going to oscillate, but at the same time, it's being modulated, okay, or sandwiched basically by the scale at here. And this is the exponential decay. So that's exponential decay here. Okay, and your sinusoidal signal essentially is going to be oscillating, okay, inside at here, okay, inside here. So it basically depends on the initial condition. It's probably going to oscillate starting from there or somewhere else. But anyway, okay, as you're going to see, it's basically a response, something like that. Okay, yeah. Okay, so the question is how fast it's going to decay to 0. It depends on what? Depends on the sigma value here, right? Depends on sigma. And sigma is negative zeta omega n. So sigma ultimately depends on the damping ratio. So apparently the higher damping ratio, and then the faster of this response, right? Yeah. So if I, in the S plane, if I do a quick summary just based on this expression, this is the pose of the second order system. Okay, so if I do a quick observation in it here is sigma. Here is omega d. Okay, here's omega d, right? Yeah. Complex poles always appear in a pair as a conjugate. So your other location in the pole is at here, huh? At here. Okay, yeah. So first thing is, as you learned in your continuous system, here's the pole sigma plus j omega d. Okay. What is the magnitude from here to here? How do you calculate the magnitude of the complex? The magnitude, yeah, it's a square root sigma squared plus this guy here, right? Yeah. So if you do a quick calculation, what's the sigma? Sigma is this. What's omega d? Omega d is this. So look at this. What is the square of this is zeta square omega n square. What's the square of this? 1 minus omega n square minus omega n square times zeta square. So when you add these two together, you got this cancelled, right? You end up with just omega n square. Then you take the square root, you omega n. So basically, the magnitude of this quantity is omega n. Okay, it's a natural frequency, right? Yeah. Okay, so I'm going to define this as a theta. Okay, so basically from this axis up to this location as a theta. Okay, as a theta here. So guess what? What will be the sine theta angle from the geometry? Sine theta, this is theta. Sine theta is this quantity divided by what? Omega n, right? And what's this quantity here? The magnitude of this portion. Is that omega n, right? The magnitude, okay, over omega n. So which means this equal to zeta. Okay. So a pair of complex conjugate poles for second order system, and that angle theta is directly related to the damping ratio zeta. So in other words, you can always write this theta equal to the arc sine of zeta. Okay, so then back to the Brad observation. Let's see. Tell me, if I have a pole at here, and if I have a pole at here, which pole resulted in the bigger damping ratio? If this is A and this is B, which one has a bigger damping ratio? A, right? Yeah. Okay, because the theta at A is larger than the theta at B, and zeta equal to sine theta. Okay, yeah, and it looks like theta is always between 0 and 90 degrees, right? Yeah. In other words, your A location will have a faster decay rate, right, than the B. Okay. But if A and B are separated by one sampling frequency. And guess what? When you map to the same location in the Z, they're actually the same, right? Yeah. Okay. Remember this observation. This is good because later we're gonna consider this case here. If I draw a reading lines from 0, out of here, okay? I draw reading lines from here to here. If I pick any point on the reading lines, what's the common feature for all the poles along this reading line? Exactly. Okay? If I'm going to draw a circle, okay, like this, what's the common things for all the points on this circle? This is an S-plane, okay? Natural frequency, okay? They all have the same natural frequency. If I draw a horizontal lines like this, and what's the common things along this horizontal line? They all have what? The same what? What's this called again? Damped natural frequency, right? Yeah. Okay. Yeah. So this is basically what happens. We are going to do next is we're going to look at some of the special curves in the S-plane. For example, like the one I draw here, this one here, the reading lines, the circle, or this guy here, and there's another one, maybe a vertical line set here, right? Vertical lines. Okay. So where does these special ones be mapped into? Okay. And then we'll basically have a pretty good idea of the mapping from S to the Z. All right? Yeah. Good. Before we look at specifically the mapping of those curves here, we need to finish the review at here. Okay, that's impulse response. Okay. The other one is a step response. Okay. So when you have a step response, okay, maybe I'll just and this is a step response, right? And very typically people summarize based on the step response. They look at it. Okay, so what's the time basically up to this maximum here, TP? What's the percentage overshoot? And what is the settling time, right? Giving a certain percentage. Maybe it's 2% of settling time, or maybe it's 1% of settling time. And up to that location, what's the settling time? Okay, that's what you summarize, and you not only summarize that, you're essentially trying to end up with a connection between the settling time, percentage overshoot, and time constant with the value of zeta and omega n, right? So here's a summary. Okay, here's a summary here. Settling time. So we use TS to call settling time. Okay, there are two kind of settling time in essence. So there's basically 2%. You settle into the 2% within 2% of the final steady value. If that's what you really want, your settling time, okay, TS, okay, is related to your zeta and omega n by this relationship approximately. Okay, for a second order system. Okay, so 4 over zeta omega n. Okay, and there's also 1%, but we typically I think we're going to use 2%. So for 1% is 4.6. Okay, over zeta omega n. All right, yeah. So essentially, you say, okay, I need a settling time of 4 seconds, for example, right, to reach that. So this is how you're going to design your zeta and omega n to meet that relationship, that requirement. Percentage overshoot. Okay. many times you don't want, okay, a very large overshoot. Okay, 30%, 20%, or 10%, right? It depends. Okay, so percentage overshoot, I'll use MP as the symbol for that. Okay, it's related to the damping ratio, and that formula is this. Okay, so negative pi zeta over 1 minus zeta squared, then time 100%. So this guy is in terms of percentage. Okay, yeah. But typically is user define a percentage overshoot. So you calculate the damping ratio zeta. So that can be calculated reversely, which is ln MP over root pi squared plus ln squared MP. Okay, so that's zeta. So for example, if MP equal to 16%, okay, you can get zeta is 0.5. Okay, now if MP 5%, your zeta is about 0.7. Okay, 0.7. So this number actually, as a control engineer, often in time you want to bear that in mind here. Okay, so a damping ratio 0.5 for second order system correspond approximately 16% overshoot. Okay, that kind of things. Okay. All right, so you also have this peak time, as indicated in the figure, TP. So TP can be derived as this: pi over omega d. Right? Omega d, we know what it is. It's omega n minus this. That's peak time. Okay. And you can also have a relationship for time constant, okay, called tau, and tau is 1 over zeta omega n. Okay. So those are very important numbers, okay, or formulas as a design control. If you design a continuous system, right? Those are typical things you have to stick to. You can also have a bandwidth. Okay, let's say BW, and or rise time. Let's say TR. Rise time is basically the amount of time it takes from 0 to 90% of the steady state value. Okay, and bandwidth, right? It's a concept basically in the frequency domain where the frequency that started to show this negative 3 dB, okay, decay. Okay, it's bandwidth. Okay. So your bandwidth typically is very much related to the rise time, okay, TR, and your TR is about 1.8, okay, over omega n, okay, approximately. Okay, so those are the numbers, you know, those are the values, the formulas for continuous system, okay, for continuous system. But if you remember what I said, your starting point is always a continuous system, and the user will give you a specification in continuous system, right? Yeah. So let's take a look at the example here. Okay. Yeah. So let's say a user saying is this: I need the percentage overshoot 15%. I need a sampling time 2 seconds. Okay. Okay. Yeah. So when people see this, you also should understand that percentage over 15, that actually means maximum, huh? Right? You can't design it for 16%. You're designing for less than 15%. When people say settling time is 2 seconds, you're not designing a settling time more than 2 seconds. You're designing for a settling time less than 2 seconds. Okay? Yeah. So using the formula, if you look at the formula here, so if you have overshoot at this, and actually I think sorry, how much? 15%, right? 15%. So I think I nailed down the 16% is about 0.5. So 15% is probably also around 0.5, right? Yeah. But you can always calculate it using this formula for the zeta, right? Giving a 15%. Okay. Okay, so that will give you the zeta is approximately 0.52. Okay, 0.52. Settling time. Let's see, where's the formula for settling? Settling time formula is this. Okay, is this. So we want, in this case, let's say we're going to use a 2% formula for the settling time. Okay, yeah. So basically, what we want is we want a 4 over zeta omega n to be less than 2 seconds, right? To be less than 2 seconds. We have zeta already, and we need to get the omega n. So omega n meaning it's going to be greater than 4 over zeta time 2, right? Time 2. So plug in the zeta here, so that gives you 3.87 reading per second. Okay, yeah, that's omega. So once you get omega n and once you get the zeta, then you can see that, okay, so if this is what you want, then the closed loop, okay, so the closed loop transfer function, right? The closed transfer function should be what? Should be omega n square over s squared plus 2 zeta omega n s plus omega n squared. Okay, should be this. Plug in the zeta omega n, okay, and then whatever it is. Okay, yeah. So you actually get 14.97 over s squared plus 4s plus 14.97. Okay, so your closed loop system should have a transfer function close to this guy. So actually, which means if this is your plant and if this is your control system, so basically you design your control system such that the closed loop system is this. Okay, yeah, that's the basic idea of a control design, right? Control design. Okay. Yeah. And the corresponding pole location in here you can calculate easily. Okay, yeah, which is about -2 plus minus 3.31, like this. Okay, G. Okay. So anyway, now if this is what you do in the continuous system, right? Continuous system. Okay, yeah. But you know, in essence, what we need is you're designing is not a continuous controller. You're designing a discrete controller, right? Yeah. So that's the next step, basically. Okay. Yeah. But before we move on just a little bit here, let's just one little bit things according to this example. Okay, so if this is a settling time like this, right? Is this a settling time? Okay, as we know that your S equal to sigma plus j omega d, and the sigma is negative zeta omega n. Okay, sigma is zeta omega n. As you can see that sigma is so related to what? To this settling time, right? Because settling time formula, you have this zeta omega n right here, right? It's right here. Okay, yeah. Okay, so which means a settling time is 4 over zeta omega n. This is your TS, and which means what? This is zeta omega n is basically 4 over how much? Negative sigma, right? Negative sigma. Okay, yeah. If you require a TS to be less than a specific number, so let's say less than 2, right? Less than 2. So that means if you do a quick calculation at here, what does that mean for the sigma value? The sigma value has to be less than -2. Okay, -2. So, and that actually means what? If your settling time is less than 2 seconds, okay, then if the question asked is, can you give, if you just look at the settling time, nothing else, okay, just the settling time, can you sketch or can you indicate the region in the S-plane that satisfy this settling time requirement? You know what I'm saying? Yeah. What's the requirement? Here, right? So how do I sketch this region again? So this is -2, and that has to be less than -2. So it doesn't matter what the omega is. So basically everywhere here, right? Like this, on the left side of that straight line. And that every pose in this region will satisfy this settling time requirement. Okay? Yeah. If you do a continuous system, let's say pole placement, right? And this is basically very typical. What you give your settling time now, then you pick a pole in a continuous system. Then where do you pick that pole in a continuous system? You know, the pole you can pick here or here, right? Anywhere over here. Okay, yeah, this idea. Okay, so now the question is, now let's move to the Z plane. Okay, to the Z plane, because ultimately, if you design a discrete controller, same idea as a continuous system. If the continuous system ends up, okay, so this is my pole location in the continuous system, and then the same question. So where will be the pole location in the discrete domain to give me the same kind of settling time or percentage overshoot requirement, right? Yeah. So what do we use? We always basically stick to this formula, right? E to the power of st. Okay, e to the power of st. Okay. Okay. So here's the idea now. S is sigma, and sigma is negative zeta omega n plus minus j omega n 1 minus zeta square, then time t. Okay, time t. That's your S, right? And then that's a t. Okay, so one more step right here, give us zeta omega n t e positive negative j omega n times t 1 minus zeta squared. Okay, that's your Z plane pose corresponding to that second order system. Okay, second order system, and in general it's a magnitude and a theta, right? Magnitude theta. So what's magnitude? R. What's the theta? It's theta. Okay. All right. So if based on this relationship right here, so what you can see, R is this, theta is this, right? Theta is this. So R is a function of zeta omega n. Theta is a function of zeta omega n. Okay, so we can actually solve for zeta in terms of R and theta, and that actually is pretty easy to solve. You can see that. So negative ln R over root ln R square plus theta square, and then you have omega n equal to 1 over t ln R square plus theta square. Okay, yeah. So that's your zeta and omega n in terms of R and theta. Okay, in terms of R and theta. Okay, so what's so good about this relationship? What's so good about this relationship is this is all we're interested in. Here's a z-plane. Maybe this is a unit circle, and maybe this is my location of this pole location in the z-plane, and it has what? It has r, and it has a theta, right? It has a theta. Okay, and then you are interested is, okay, so for this particular location, what will be the corresponding damping ratio and the natural frequency in the s-plane, right? In the s-plane. So here, okay, here. If once you have this z and an omega n, you can derive. Okay, so for this location in the z-plane, and then I would have this much of overshoot, and this much of settling time, and this much this and that, right? Yeah. So these two formula, right, essentially is sort of the guideline we'll see. We actually use this in the pole placement design in the previous lecture. This was an example we did that, right? Yeah. I think I'm going to stop here. There's one example we'll go over in the next lecture, and then we'll also look at all the special curves in the s-plane. How would that be mapped into that plane, and what would they look like in that z-plane? Okay. Yeah. Any questions? Okay. So we'll see you next Wednesday. Okay. So come a little bit early, so then you can start early. You can have a little more time if you want. Okay. Yeah.